Hello and welcome to the Laboratory for Quantum Guesses, where we are using atoms and photons in order to understand the way matter behaves when it's ruled by quantum mechanics. Think about this axis as being energy or temperature. When you go to high energy, you're breaking matter into smaller and smaller pieces, like atoms broken into electrons and nuclei, and all the way down to the most elementary constituents of the universe. When you do the reverse process, you go to low energy or low temperatures, you're organizing matter into structures. Say gases first acquire a volume by becoming liquid, then they acquire a shape by becoming solid. But if you go down to the lowest energies, you have more and more exotic properties like superfluidity, superconductivity, and even more complex states of matter. And this happens all the way down to the quantum mechanical ground state, or another word to say zero temperature. We know that we cannot access this particular state, and in many cases, we actually have no clue how matter looks like around this area. But what we know is that these properties that happens there, they have a universal character. That is, they only depend on a few parameters, and hopefully, if we can take a system and shape it in such a way that it acquires these parameters, then we will be able to look at it and learn how matter actually behaves in this crazy regime. This approach is called quantum simulation, and this has been designed and invented in the 80s, mostly by Richard Feynman, who envisioned a machine that could imitate any quantum system, including the physical world. That was, of course, in the 80s a dream of a theoretician, but with progresses, in particular in atomic, molecular, and optical physics, this is becoming more and more a reality. In my group, we are using quantum gases, that is, gases of atoms cooled down to nanokelvin temperatures to realize such quantum simulation. This is the way it works. Starting with a vapor of atoms at high temperature, we collect and cool a cloud of atoms using laser cooling and trapping. This creates a dilute gas at about millikelvin temperature, which we hold otherwise in ultra-high vacuum. We then capture the atoms using an optical trap and then turn on a high magnetic field. This magnetic field is making the atoms strongly interacting with each other. Afterwards, we are simply evaporating the cloud. That means getting rid of the atoms that have the highest energy. In several steps of this evaporative cooling, we're left at the end with extremely cold gases in the nanokelvin temperature range where all the quantum mechanical effects manifest, such that the Pauli exclusion principle or Bose-Einstein condensation. Then we send light onto the atoms, specially tailored in order to program the quantum simulation and control the way atoms interact with each other. In practice, this is how a quantum simulation machine looks like in the lab. It's a quite complex arrangement of optical elements to carry all the laser beam onto the atoms, vacuum and mechanical systems, electronics, and computer control. As a student in our lab, you may have the chance to learn mechanical design and assembly, to learn optics, laser physics, but also electronic design and assembly, as well as computer programming and simulations.